Hello GGS300, welcome back. Today we're going to be going over what is the fifth lecture, so essentially we're going to be focusing on probability. Just before we begin, I just want to give you a bit of a little update about where we're at within the course and what you should be expecting over the coming weeks. So essentially the fourth assignment is going to be set this week, and very shortly I'll then be putting up a set of tests. Those tests are basically ungraded, but they're basically going to prepare you for the midterm exam. So within those tests, I'm able to work out how well you've been absorbing the different pieces of work that we've been focusing on, and also you are able to identify what you have and haven't actually absorbed, and then you're able to work on those gaps. So basically doing those tests before you take the midterm is absolutely essential, and if you skip them, then you'll be in a really kind of bad place to actually take the midterm test, so definitely do not do that. Okay, so the midterm will be going live next week, so there's no assignment for the week commencing the 1st of March, and therefore I'll be setting the midterm that week, so you could get the tests and the assignment done that week and any revision that's actually required. So I think that should be fairly succinct for you. And then I think the important thing to say is that this is actually the last lecture for part one. So if you remember, if you go back to the syllabus, essentially what we had in those first few weeks was introduction to spatial statistics, descriptive statistics, and then basically we went all the way up to probability, which I'll be covering today. And that's the portion that you're going to be tested on. And it's a really important part of the course because it kind of lays that foundation that everything's going to be building on, particularly the content that we're going to be covering today, as we move towards doing inferential testing, particularly kind of more simple inferential tests that we'll cover in the next third of the course, and then it starts to step up again as we get to the final third, where we start to cover more complicated techniques like multiple regression, for example. Okay, great. So let me know if you've got any queries. Hopefully that's nice and clear. Hopefully you've got the hang of now how you actually access the course material on the Blackboard website, how you submit that course content, and hopefully, I hope you're enjoying the course and you're actually learning this, what is very important content for your own professional development. So today I'm going to be focusing on introduction to probability. It's going to be reasonably gentle in the first part, focusing more on definitions. It starts to get a bit harder as we get through to the second part of today's lecture, and then we're actually going to cover practically how we carry out some of these techniques within the laboratory work, which will be in the second video. So basic probability, what is probability? Well, it's the chance or a likelihood of a particular outcome occurring, okay? So we have a range of different processes which exist within the world. So here I'm talking about deterministic processes. In a second, we're going to talk about random stochastic processes as well. So within the spatial sciences, we don't have that many deterministic processes. Ideally, a deterministic process is one that can be described or predicted with certainty. So there's no randomness there in the determination of future states. So, I mean, at a very basic level, deterministic process might be if you have a tank of water and you place a weight in that tank, each time you place the weight in, you will be able to predict the amount of water, the height of the water within that tank. Okay, so and that would be proportional to the amount of water which that weight displaces. That's an example of a deterministic process. So it's based on those immutable physical characteristics that are common to physics, I mean, it's great for those types of scientists who can work in this way, but actually in spatial sciences, because we have human behavior, there aren't exactly too many examples where we have these kind of perfectly predictive physical patterns. So I'll give you some examples of deterministic processes here. So maybe it could be models of the Earth, so determining daylight and nighttime hours. Newtonian physics, it could be the movement of objects or of planets in relation to their size, the physical forces between them. Or it could be based on Maxwell's equations, so the behavior of waves, light, radio, ultrasound. So these are all waves on the same electromagnetic spectrum. They're just at different frequencies and therefore they have different physical properties. Okay, So this just gives you an example of the electromagnetic spectrum that we all engage with on a daily basis. So the light that we view is visible light. The radio that we use to send data and receive data over our cell phones is in a different portion of that wavelength. And generally, we could set up experiments where we wanted to measure the physical propagation of radio waves, or the speed at which these waves move, for example, for light. And we would be able to set up these experiments and basically get the same results time after time after time again, providing we control for those other variables that might affect changes. So basically, we have very strong predictability. These are deterministic physical processes, and that's a very nice, kind of beautiful thing. It doesn't happen too often within the spatial sciences, unfortunately. Probabilistic processes, therefore, are those spatial phenomena that essentially can be described and predicted by likelihood and some degree of uncertainty. Okay, so there's two types. One is a fully random process. So imagine you have the same probability assigned to all outcomes. So we'll talk a lot later in very basic terms about how you might make an estimate for the probability of an outcome of tossing a coin or rolling a dice. They all have the same probabilities assigned to those outcomes. Whereas stochastic processes basically are where you have a predictive component, which is deterministic, and then you have an uncertainty kind of random amount. And when you put them together, it means that you don't always have a very easily predicted process. So it's kind of a halfway house between the deterministic process here at one side of this very simple diagram I show you, and then the random processes at the other side of this diagram. And the stochastic processes sit in the middle here. So just think of them as semi-random. Okay, so I've talked before about hurricane trajectory modeling. That's a good example of stochastic process. And therefore, when we actually model these phenomena, we basically have to build some of that randomness into our models based on understanding the distribution of different particular outcomes. Okay, and that's how we're able to create simulations of physical entities which actually map the real world behavior of some of these processes, whether it's weather systems or fluvial flooding, whatever. We're able to, in a very robust way, start to model how the world exists around us based on these kind of principles of understanding determinism or probabilistic outcome. Okay, so what is probability? You know, we've been through that. It's the likelihood of a particular event or outcome actually occurring. Essentially, we can write that in math notation. So PA, so the probability of A, can be defined essentially based on f of A, which is the absolute frequency for a particular outcome occurring, or f of E, which is the frequency of all of the outcomes occurring. So just bear with me on this. I'll explain this many times, and hopefully you'll get an understanding for what this means. It's always a probability, a number between 0 and 1, okay? And you can think of that however you like, but I like to think of it in percentage terms. So just going to the dice example, imagine if we were going to roll a die. My question to you is, what's the probability of getting a 6? And actually, if you took the equation which we have above, and then we wanted to work out the probability, well, the absolute frequency for getting a 6, well, there's only one potential outcome out of those 6 sides, which is a 6. So 1 is the numerator. And then on the denominator, where we want the frequency of all outcomes, we would have 6, because that's all the different potential outcomes. So if you divide 1 by 6, you get 0.167, or, as I like to think of it, 16.7% likelihood that you would roll the dice and it would land on the 6. Okay, so just think of it in terms of, you're going to be doing that equation, so it's 1 divided by 6, and when we do that, we get 0.16. Okay, 6 reoccurring. And the point of that, the point of me showing you in this way is it gives you an understanding for why it's going to be occurring between 0 and 1. So if it's 0, it's never going to occur with certainty. If it's 1, it's going to occur every time with certainty. And then if it's in between those ranges, then there's a probability of that particular outcome occurring at some point. Okay. Great, so I've provided just another more realistic example for us down here. Maybe we're interested in doing some hydrological modelling. Maybe we're just interested in general weather patterns. So we have the number of wet days and dry days. So out of 100 days, we have 38 that are wet, and we have 62 which are dry days. So then we're able to calculate the probability of it potentially raining in any day. So essentially what we do is we want to find the probability of a wet day, PW, and then to do that we would need the absolute frequency of wet days, which is 38. We would then need the F of E, so that's the frequency for all outcomes. So essentially that's the wet days plus the dry days, so that's going to be 100. And then we would need to divide the 38 by the 100, and that gives us 0.38, which basically provides us with a 38% chance that there might be wet weather on any particular day. Okay, so this is kind of very simple math. It's just a very simple equation. It's more that you kind of need to understand the terms that we're using. So I know it's kind of scary when I start talking about things like absolute frequency or what the frequency of all outcomes is. I'm afraid that you just kind of need to learn the equation, and then hopefully that will kind of cement in your mind that what we're trying to get here potentially is a probability for an event occurring in the future. Okay, so a lot of what we've done in the past when we've been looking at histograms, that is an outcome of certain event processes. Imagine that now we want to flip that thinking on its head, and we want to say, okay, well, now I've got that data. What's the probability of an event occurring in the future? And that's incredibly powerful. Okay, if you look at all the jobs which are paid very well, those jobs that work on forecasting are generally very well paid jobs, and this is totally an area that you want to get into. It's fine for us to make a GIS map, a pretty map, fine, but the reality is that what you want to do is you want to have predictive models, forecasting models, and actually the GIS bit is just the afterthought. It's just a software technique that does a lot of the processing, and then you have that math model that provides you with some sort of understanding of a process in relation to its future state, and that's really where all the good stuff happens, the good science, as well as in industry and government, where all the some of the most exciting jobs are. So when I talk about absolute and relative, let's just go over those terms very quickly. So when we talk about the relative frequency, really what we're talking about here is we define this as the ratio between the absolute frequency of an outcome and the frequency of all of the outcomes. Okay, so I touched on this previously. The absolute is the actual number of times the outcome has occurred, so it's the raw number. And then the relative relates to the frequency of all of the overall number of events. Okay. Probability for the relative frequency. So essentially, one of the issues that we have in calculating the relative frequency is the sample size. Okay, so there's a lot of uncertainty when you have small sample sizes. It affects the probability estimates that you make, and that means that you could be less robust about a prediction which you may need to make, and you might have a lot of money riding on that prediction. so there's a lot at stake here. You need to make sure that your method is robust. So imagine that we toss a coin and we know which side lands upwards. It's impossible to predict the outcome, heads or tails, in advance with certainty, but then again we can run experiments to understand what the probability might be of one particular outcome over another outcome. Okay, so we can keep tossing the coin again and again and again, and the proportions of the outcomes that land on heads or the proportion of the outcomes that land on tails can help us understand this relative frequency. Okay. So imagine we had this experiment that we were setting up. We have a set of fixed conditions. We're interested in repeating that experiment based on n repetitions, so for our sample, in order to understand the likelihood of an event occurring with frequency f, okay? And then we're going to calculate the ratio, the Fn relative frequency, to understand the potential outcome of that event. So here in the table, what we have is the number of repetitions that we have in each of our experiments. So just imagine each row here is an experiment. And in the first experiment, we toss the coin 10 times. In the second experiment, we toss the coin 100 times. In the third experiment, 1,000 times, so on and so forth. And then each time we write down the number of heads that we actually obtain in the row values here. So in the first experiment, we get 8 out of 10 heads. In the second experiment, we get 62 out of 100 heads, so on and so forth. And then we calculate the relative frequency. So when we have a small number here, actually it's quite skewed. It doesn't appear at first glance that this is a 50-50% breakdown of the probability, which you and I know a priori, because we've tossed a coin before. We know that there's going to be, if it's a balanced coin, the 50-50% chance for each outcome. So this really kind of demonstrates that at small probabilities here, you end up with quite skewed relative frequencies if the sample size isn't large enough. And then actually, if you look down each of the experiments where we increase the sample size, you'll see that what we get is a convergence of the relative frequency towards that 50% mark, okay? And this is going to be incredibly important for kind of how we design sampling exercises, sampling strategies for when we need to go out and we need to get information from people or houses or ecosystems in order to inform our some experiment that we're running, for example. So sample size is really important. You need to pay attention to it so that we can get some sort of understanding of the relative frequency. Okay, probability terms and definitions. So, if we're going to run an experiment like I just told you, then that would be a set of procedures which give rise to a set of data, as I explained previously. We have a sample space within there, and that's the set of all possible outcomes that could occur. Each individual element from the sample space could be treated as an elementary event. And each time we run a trial of the experiment, that's deemed, in this case, a trial or an iteration, and then we basically end up with an outcome, which is one or more elementary events of an experiment. So what I've given you there as a list is basically the definitions that you need to know in order to understand these different aspects of understanding probability. And then in this table, what I've done is I've just given you an example of that. So imagine the experiment we want to run is understanding what the probability is of actually getting at least 1/6 when rolling 2 dice. So the sample space could basically be all of the different outcomes that we could get. So you could get on dice 1, you could get a 1. On dice 2, you could get a 1. On dice on the second run, you could get a 1 on dice 1 and a 2 on dice 2, so on and so forth. Okay, so this is just all the possible outcomes that you could get, the whole sample space. This is what we want to explore when we start rolling the dice. And the elementary events are basically those events which fulfill our experiment criteria. So you'll notice here they all basically have a 6 in because they fit the experiment aim, something that can occur, you'll see in the definition up here, so it's containing the 6. And then the trial is basically rolling the die twice. So we maybe we carry out 10 or 100 or 10,000 of these trials in order to develop an insight into the probability of this outcome. And then the outcome could be from a single set of die that are rolled, a 2 and a 3. Okay, and that either does or it doesn't meet the outcome condition that we're exploring. Or you could do the same if you're interested in the probability of more than 60 inches annual precipitation, and therefore the sample space would be any real number over 0 or equal to 0. The elementary event would be any event that's over 60 inches of annual precipitation. The trial would be a whole year's precipitation record, and an outcome could be a value which either does or does not meet that particular experiment target. So for example here it's 63.5 inches of precipitation. Okay, so there we have some definitions, and I've given you an example of what those definitions mean in different contexts. We do have rules then of probability, so this is something that we will end up covering within the lab. So here, I just want to highlight before we get started that you'll remember from the previous slides, a probability, because of the way that we set up that relative frequency, is going to be between 0 and 1, okay? So it could be equal to 0, it could be equal to 1, or it could occur anywhere within that space. So that's essentially what I'm re-emphasizing up here. And because we know that, it means that we can actually carry out particular processes for different types of events, okay? So statistically independent events, mutually exclusive events, or non-mutually exclusive events. Before we begin, it's important for me just to emphasize that if we have the probability of a heads being achieved from just flicking a coin in the air, there is a complement probability for the other outcome that could occur. So if it's a 50% chance of getting a heads, then the complement probability, as I demonstrate here, would be 50% for the other outcome. And actually, if you added those two outcomes together, so if you add all of the different outcomes that could be achieved together, then you would end up with 1. Okay, that's based on the whole math framework. So all of the different outcomes basically sum up to the value 1. Okay, so that's all the potential outcomes that we could achieve. So now I've just kind of explained that, let's dig into some of these different types of events and how we would calculate probability. So there are rules, and we just need to learn the rules, unfortunately. So basically, for statistically independent events, this is where if I flipped a coin, the second time that I flipped that coin, flip the coin, it would not depend on the state of the first outcome. Okay, so each time that I flip it and I'm waiting for either a heads or a tails, it's completely independent of the previous trial that I had, which was either heads or tails. Okay, so this is somewhat different from, for example, one of the previous projects that I was on. We were modeling infrastructure systems and we were modeling water resources. And it would be somewhat different from an example where we had reservoirs in that water systems model, because actually the amount of water that's in a reservoir in a particular year is actually highly dependent on the value that you had of water in that reservoir in the previous period. And that's an example of a statistically dependent event, and therefore you need to be conscious of that when you're actually designing the modeling probabilistic framework. Thankfully, we don't have to worry about that here. This is independent events, so this is kind of a very simple way to think about probability, and that means that we can do quite simple calculations for how we would come up basically with the probability of 2 statistically independent events. So here you can look at the equation. So what's the probability of A and B occurring at the same time? Well, then you can just get the probability for A and the probability for B, and you can multiply them together, and that will give you the probability of those 2 events actually occurring, providing they are actually independent. So imagine that we're interested in getting the probability of flipping a heads and then a tails in order. So what we want to do is we want to find this P, the probability for a heads and then a tails here. We need to take the probability for getting a heads and then the probability for getting a tails. We need to multiply them together. Obviously, we know a priori that there's a 50% chance of flipping either a heads or a tails, and therefore if we're interested in 2 trials and we're interested in the probability of having a heads and then a tails, then basically we would need to multiply them together. Okay, so that's 0.5 times by 0.5, so let's do that in the calculator. 0.5 times by 0.5 is going to be 0.25. Okay, so I don't learn that easily. If you just showed me this and I didn't know it already, then this wouldn't be the best way for me to digest that information. And particularly with how hard it is for us to do this asynchronous, you know, we can't be in the lab together. You aren't able to quiz me on points that aren't clear to you. I'm not able to put you on the spot to answer questions that I might have, and therefore the learning process is kind of hindered. So I thought what I would do is just kind of sketch out an event tree for these different outcomes based on that very simple example which I gave you previously, okay? And this is a fairly standard way to understand these types of events, so you can develop event trees. If I was designing the Dragon crew craft for SpaceX to go to the International Space Station, then they will be taking event trees for failure rates, and they will be interested in all of the backup systems which provide support to those basic life systems that you need when you're on a spacecraft and you're going into a vacuum where you've got no air. So essentially this is one of the techniques that they use, but I've just very much simplified it here. So just going back to the example, we're going to start and we're going to be interested in the first flip as to whether we get a heads or a tails, and the probability at this stage is either 0.5 or it's 0.5. Then we get to the second flip, and then actually we have another 0.5 probability for each of these. You can see we wanted a heads and then a tails, so that's how we ended up with these two probabilities here. And you'll remember that the outcome was 25%, so it's a quarter, and actually that obviously equates to all of these 4 different outcomes that we could have had here in the event tree. So you see, if you added all of these outcomes together, we would have got 1, which, as I explained before, is representative of the full event outcome space. Okay. So that was the first type of probability for independent events, basically. What happens if we have mutually exclusive events? So there's no overlap between those events. The events can't appear at the same time. What if we want to calculate the probability of these happening? So essentially the rule is that the probability of A or B taking place at the same time, is PA, so the probability of A plus the probability of B. Okay, so the key point here is OR. The use of OR means the pick is successful if either one of the 2 conditions is met. Okay, so I'm going to go back to my favourite example, which is obviously dogs. So I'm going to ask you here what the probability is of actually picking a Labrador or a Golden Retriever out of all of those dogs that are running around in the park having fun. So let's just have a look at those dogs that are in the dog park first. So imagine we've got, let's say that they're American Labradors, we've got 4 of them. Let's say we've got 2 German Shepherds, 2 Golden Retrievers, we've got 1 British Bulldog, and then we've got 1 Poodle. So essentially my question is, what's the probability of you picking at random out of any dog running around, either a Labrador or a Golden Retriever, okay? Which means that we basically need to get the probabilities for those 2 different breeds out of the total number of breeds that we've got within the park, okay? So basically we need to get the lab probability, well we've got 4 and we've got 10 different outcomes, so the probabilities of picking this one breed is 4 out of 10, so 40%. And then we're interested in the Golden Retriever, where we've got 2 different dogs here, which are Golden Retrievers, so that's 2 out of 10, that's 20%. And because these are mutually exclusive events, we can add the probabilities together. So 4 over 10 plus 2 over 10 equals 6 over 10, which is 60%. Okay, so we've got a 60% chance of picking any dog out of the park at random, and it basically being either a Labrador or a Golden Retriever. Okay, and this calculation works because you can't simultaneously be a Labrador and a Golden Retriever at any one state in time. Okay, so the outcomes are exclusive. Okay, so rules of probability, and this is for non-mutually exclusive events. So there is overlap that's possible. Okay, so maybe I asked you the probability of picking a Labrador or a black dog. Now we need to take advantage of the rule that I specified up here. So what's the probability of A or B? We need to make sure we get the probability of A and the probability of B, add them together, and we need to subtract the probability of it being potentially A and B. Okay, so let's do that now. So we want to find the probability of picking a Labrador that may also be black. Sorry, a Labrador or a dog that's black. I think I should just specify that so it's really clear to you guys. So what that means is we need to get the probability of a lab, which here, based on this data, so we've got 10 dogs, and we've got 4 Labradors, so it's 4 out of 10, 40% chance of getting a lab. And then we need to get the probability of getting a black dog. well, there's 2 black Labradors and there's 1 black poodle. So basically that's 3 out of 10. So there's a 30% chance of getting a black dog. And then what we need to do is we need to find how many are labs and also black. Okay, so when we do that, we find that there's actually 2 Labradors that are black. And then that means that we can add together our initial probabilities, which are 4 over 10 and 3 over 10. So we get 7 over 10. And then we need to subtract those cases that are both Labrador and black. So that's 2 over 10. So we subtract 2 over 10 from 7 over 10 and we get 5 over 10. So it's a 50% chance of us picking a dog and it being either a Labrador or either a black dog. Okay, so hopefully that's provided you with a little bit of an overview as to how we carry out these 3 types of probability assessment for different events, depending on whether they're statistically independent, depending on whether they're mutually exclusive, or depending on whether they're non-mutually exclusive. Let's move on now onto probability distributions. So what is a probability distribution? Well, this basically is where a set of outcomes can follow a consistent pattern. So it's really important. If we know then what the shape of the pattern is for these different events, then we can use it to our advantage to make predictions, for example, for future event outcomes. Okay, so this is very closely related to frequency distributions, as we covered in the previous lectures when we covered histograms, but this time we can use it as a way of estimating what the potential outcome may be in the future based on different types of events. Okay, so we can define this probability distribution as a table, a graph, or a mathematical function that describes the potential value of a random variable and their corresponding probabilities. So we covered previously frequency distributions, histograms, so where the y-axis shows the number of occurrences. Just imagine now that we've changed this so the y-axis actually shows the probability of occurrence. So imagine we had 2 die and basically we were rolling them. Essentially, we would end up getting some sort of distribution like this because they're normally distributed. And basically we could then use that as a way to inform the likelihood of us getting particular outcomes in the future. Okay? So what is a probability distribution? Okay, well, we've covered this already. There's 2 different types there, and I'm going to cover 3 distributions from these 2 different categories within this lecture now. So discrete, that's basically where you have discrete integer values. So these are just complicated ways for saying think of them as whole numbers. And this is important because if you think of a person or the number of people or the number of hurricanes, you can't have 2.5 people or 2.5 hurricanes. So as a consequence, these are discrete events. You're either going to have 1, 2, 3, 4 in these particular outcomes. And we have particular probability distributions for these, so either binomial or Poisson distributions. Then we have on the other side continuous distributions where the number of outcomes are infinite. So for example, if I just told you if we picked a number at random, I mean, that number could have an infinite number of decimal places on, okay? So that's why the outcomes are potentially infinite. If I told you to pick pi, you could calculate pi out to 20 million decimal places. So basically, this is why it's continuous. You can have a very, very large number of potential outcomes. And actually this type of continuous distribution is based on the normal distribution, which you may have heard of before, or a bell-shaped curve because it looks like a bell. So we'll be covering this in the second part of the lecture. So let's start now on binomial distributions. So this is where we have a discrete outcome and there's only 2 potential options for each outcome. Okay, so this could be yes or no, this could be true or false, it could be success or fail, or 1 or 0. There's only 2 outcomes for these events, okay, for the different trials that we have, but you might be interested in the string of different trial outcomes that you get and the probability of those potential outcomes. So this gives you an example here of whether a person is either employed or unemployed, whether a river is above or below a specified flood level, or whether a respondent to an opinion poll either favours or opposes a particular issue. So we're interested in the sequence of these binary outcomes, and actually the easy way to remember binomial distribution is because it has bi in front of it. And if you go back to it, well, it's probably either Greek or Roman. Bi relates to bicycle, binoculars, so it's quite easy to remember that these are two potential outcomes that we're dealing with here. There's a set of assumptions around when you use a binomial distribution, okay? And so you have to have met the following conditions, and there's no easy way for me to cover this other than to just go through the list of assumptions and make you aware of them. They are in the book, which obviously you need to read to accompany this chapter. But just imagine that there are repeated trials, and each of which can result in only one of two outcomes. Okay, so we've covered this before: fail or success, heads or tails, rain or no rain. The probability of one given outcome is constant for all trials over time, and it's denoted by P, the probability. The complement probability of the outcome is denoted by Q. Okay, this is fairly easy. We've been over this before. So I covered the complement probability earlier in the lecture, so you can get Q easily if you know P. You just subtract P from 1, and that will give you the complement, because obviously P plus Q equals 1. And the trials are independent, and the number of trials is denoted by N. Okay, so the outcome follows a binomial distribution based on parameters P and N. Okay, now this looks hideously complicated. Do not worry, we will cover this many times, and really what you need to understand is the general thrust of how you calculate this, rather than being able to kind of explicitly calculate it off the top of your head. We will show you within the lab. I will do how you do this manually, and then also how you use just the inbuilt functions. So when you actually come to needing to use these, you can just use the inbuilt functions. All you need to know in this stats class is basically overall how this general binomial distribution is used, understood. That's really the type of understanding that I'm looking for, and you'll be tested on using it in order to generate particular answers. So hopefully that's fairly straightforward for you to do. So we want, using this binomial distribution, the probability for a given outcome occurring x times in n trials. So we want to get the probability of x. So x is the number of times the given outcome occurs within the n number of trials. We then have n, the number of trials, as I explained before, p, the probability of the given outcome, and q, which is the complement probability. And don't be scared off by the exclamation mark. This just means it's a factorial. So basically, if we have n, the n factorial, that's just looking across the sample space. So it's how many different potential outcomes could there be. So if we're interested in, if we've got 5 trials, then there could be 120 different potential outcomes that could occur based on whether it's yes, no, each one of those stages, okay? So we could go out by hand and we could run an experiment where we meet all of those different criteria and calculate this, all of the unique independent number of trials that we could get. In an experiment. But the point is that we don't need to do that because we have the factorial here, so we can actually just calculate that. So to get the factorial of n when it's 5, we just times 5 by 4 by 3 by 2 by 1, and we get 120. Okay, so this is the total number of possible permutations that is available for what we're interested in. So that's very high level. Let me give you an example now and show you how we actually use this. So imagine that you're a vegetable grower and you're interested in starting a new business. You need to find a location to do that vegetable growing. Basically, you need to select a site that has had enough rain so that you don't have to use irrigation every year, because irrigation is very expensive. You have to pay for the water. Within the water, you have to pay for the processing of the water, which uses power, so it releases a lot of carbon, so it's expensive and it's bad for the environment as well. So really, you want to kind of be aware of this if you're going to basically produce what, at times can be quite a low margin product if you're growing vegetables. So the grower can actually only afford irrigation 1 out of the 5 years, so this is important information for us. One potential site has been found. It had enough rain for 21 out of 25 years, so the probability for requiring irrigation is 4 over 25, so 0.16, which is 16% probability that we require irrigation. Okay, so the question then is, well, what's the probability a grower can meet the requirement for irrigating only 1 year in 5? Because that's basically that's the amount that is able to be spent on irrigation without breaking the profit margin down. Okay, so the binomial example, what I've done here is I've run through the equation, run through the question, and I've provided this table for you, and actually this table can just be recreated in Excel if you want to do that. I've put the numerator and the denominator equations down here for how you calculate this in Excel. So what's the probability a grower can meet the requirement for irrigating only 1 year in 5? So the number of years that we have is 5. The probability of meeting the irrigation requirement is 4 over 25, so 0.16. The complement is 0.84 x here, which is the number of times the outcome occurs within the trial. Is 5 because we're interested in 5 years, and we've got the factorial as well, which is 120. So basically for each of these parts of the equation, I've written down all of the different numbers that could be used in order to then calculate the numerator and the denominator. So you've got the inputs for the equations, you've got the equations, and then we've got the numerator and the denominator, which generates this probability. Okay, so here for no irrigation, there's a 41% chance. For just irrigation in 1 year, there's a 39% chance. For irrigation in 2 years, so this would be where it'd be unviable, be 15% chance, etc., etc., etc. Okay, so I've just put those binomial probabilities in here into a table for the number of years out of 5, and I've listed whether the outcome is suitable or not, as the case may be. So if there's no irrigation required because we don't need irrigation in those 5 years, great, there's a 41% chance of that. Let's hope that's going to be the case. For 1 year of irrigation, we've got a 39% chance, and then as we get into 2, it becomes unviable. So you could either present the result for where there's just 1 year of irrigation required, 39%, or you could add these probabilities together essentially, and then that would provide you with the cumulative probability of requiring irrigation for only 1 year in 5. Okay, so that would be about 82% or something like that, 81, 82% if you were to add these numbers together. And you can look at the actual distribution of these binomial probabilities across the 0, 1, 2, 3, 4, 5 outcome fields against the probability. So this is generally how, if you're going to look at binomial distribution, you might see it more as a shape of a curve that basically follows the top of these different bar plots that I've placed here. Cumulative probabilities we can also calculate. So in the previous example, we were focusing on the likelihood of a particular outcome taking place. Here we want to know what the cumulative probability is up to a certain outcome. Okay, so I touched on it very briefly in the last example when explaining it, but here I use an example of just flipping a coin 10 times. Okay, so let's say I'm going to go set you off, carry out an experiment, and I want you to basically flip that coin 10 times, and I want to write down how many times you got 7 or more heads, and I wanted you to repeat the experiment 10,000 times. Essentially what we could do for all of those times where you got 8, 9 or 10 heads, then essentially you could add them together in order to get the probability, the cumulative probability for exceeding 7 heads, okay, across those different experiments. So hopefully that's fairly clear to you. We'll kind of pick up on this within the lab work. We can generate the binomial distribution in R using a variety of different functions. So you'll see here that binom stands for binomial, but then there's a variety of different ways that we can use the binomial. We can use the density, where basically we're interested in getting the probability of exactly X outcomes. Or we could get the cumulative probability of getting up to X outcomes. We could get the quantile probability. So basically, what X value do you need to get for a certain cumulative probability? Or we could use the random binomial. In essence, what we're going to be doing quite a bit is using the quantile function, and I'll show you how we do that within the lab work. Okay, let's move on to the Poisson distribution now. So this is a less clear name, whereas binomial had a very kind of clear way to understand what it was doing because it has by in its syntax, and therefore it's kind of indicative of the fact that we have either only two outcomes. Poisson, well, it's named after Simeon Denis Poisson, obviously French. So he was the person who came up with this distribution. And we can use the Poisson distribution when we have a set of conditions that we actually are able to meet. So the events are actually countable as a set of whole numbers, so they're discrete. So remember I explained before, you can't have 2.5 hurricanes or 2.5 people. So you have to have discrete numbers, 1, 2, 3, 4, 5. You can't have decimal places. We then need event occurrences that are independent. We need a fixed time interval or space, so for example 1 year. And then we need the probability of the event within the certain interval to not change, so it's homogeneous probability over that set time period. The probability of observing a single event within a small interval is proportional to the size of that interval. I mean, that makes sense. If I if I said to you what the probability of you getting a phone call is, if I start to change the time period, it's going to end up changing the probability of you getting one, whether I say in the next 10 minutes, in the next hour, in the next day, in the next year. The probability is going to change as a consequence of that. And also the probability of two events occurring in a small enough time interval is negligible. Okay, so those types of conditions we're going to have for many of these different statistical approaches, and I'm afraid that you just need to learn them because you might be tested on them. Poisson distributions, so basically this is where phenomena exist randomly in spatiotemporal ways, and they can be measured as frequencies. So I use these in my work if I'm looking at the number of phone calls or the number of data accesses that users on cell phones may be using when they're in a specific cell tower radius. So maybe I'm interested in how many people are streaming multimedia video in the busiest hour of the day, because that's going to place the largest amount of capacity on the cell tower, and therefore I need to understand in a spatial framework how often there's going to be particular demand placed on that cell tower, and I need to have some sort of understanding for that. So you can think of this as the number of lightning strikes per unit area, or the number of cell phone calls that are being made in a specific quadrat area. We could also think of this in terms of the number of school day cancelled per year, so maybe due to snow, the number of visitors visiting a national park per day, the number of hurricanes sadly hitting Florida per year. Okay, so this is one way that we can use the Poisson distribution. It's actually arguably easier to calculate the Poisson distribution because the actual formulae is a lot more simple, I think. So for the probability of an outcome occurring x times p of x, we basically need the lambda value. So this is the mean frequency of the event raised to the power of x, so the frequency of occurrence, divided by the natural logarithm raised to the power of the lambda value multiplied by the factorial of the frequency of occurrence. Okay, so that sounds super complicated. I appreciate it starts to become daunting if you're not used and if you're not comfortable with math, but basically we'll cover this in the lab in a very simple way. You just need to understand that this is the math formula. I'll provide you with examples of how we calculate these outcomes, and hopefully that's clear to you once you've been able to see the theoretical math and the way that we calculate it multiple ways in the lab class. So the Poisson distribution characteristics, they're very good at describing the distribution of rare events, so car accidents, for example, or the probability of you getting a very rare disease. They're not great at describing events that occur very commonly. I've explained before that they're discrete, so you can't have half an event. You kind of know that you're dealing with a Poisson process if you're dealing with mean frequencies. Okay, so if you're talking about the occurrence of something per year or per quadrat or a rate, that might be a Poisson distributed process. The occurrences should be randomly across space or time, and technically you can have an infinite number of discrete outcomes. Okay, so I use the example here that we might be interested in how many days Mason had to sadly cancel teaching, probably due to inclement weather. So for example, that might be an average of 2 days per year, but then there's a probability of any one year having up to 10, 25 or 100 cancelled days, which is kind of ironic because this was obviously written pre-COVID, and actually if you wanted to think that, you know, at times we've had to cancel pretty much the entire semester to work remotely, very sadly, then there is a very, very small probability, which has actually come true, that we could have, you know, up to 100 cancelled days, sadly. So I hope on that kind of pessimistic outcome that we'll all be able to be in person together, enjoying each other's company next semester. So give me an example of this. Ed, I don't understand the formula, it's still too abstract. Please help me understand this in kind of very basic terms. Okay, let's take Florida, let's take the hurricane season that it has to experience every single year. Let's take the data for the past 104 years, so essentially 1900 to 2003. Florida was sadly hit by 24 major hurricanes, and the number of hits per year follows a Poisson distribution. Okay, so my question to you is, well, what's the probability that Florida will be hit by at least 3 major hurricanes in any particular year? Okay, so what we need to do is we need to get our Poisson distribution formula. So P of x equals this particular formula here, which I covered in the previous slide. To get P of x equal or over to 3, what we need to do is we can take 1 as the total number of outcomes, and we can subtract the probability of the events which are hurricanes hitting Florida, either none hitting or 1 hitting or 2 hitting in a year. So all those events that take place below 3. Okay, so what that means is, as I've demonstrated here, is we can go 1 minus P0 plus P1 plus P2. Okay, so we need to do this first, it's in brackets. To get the probabilities for all of these events, then we need to subtract it from 1. So how do we do that? Well, we can, for each iteration of those values, for no hurricanes, 1 hurricane, 2 hurricane, we can basically run the formula that we have for the frequency probability. So, for example, if we take 24 and we divide it by 104, we get 0.23 as the relative frequency, and then we can run it through the equation here based on the number of events occurring. Okay, and we get 79% for no hurricanes hitting Florida. We get 18% for 1 hurricane hitting Florida, and we get 2% for 2 hurricanes, sadly, for hitting Florida in the same year. So essentially then what we can do is we say, okay, well, what's the probability for us getting 3 or more hurricanes, which is the point of this particular question. We can subtract the sum of those probabilities, so P0, P1, P2, and then we can subtract it from 1, which is the total number of event outcomes. And what we end up with is 0.17% probability of there being 3 or more hurricanes hitting Florida in any particular year. So obviously this here is the probability, 0.0017, which we can interpret in percentage terms as 0.17%. Okay, so hopefully that's somewhat clear to you. If it isn't, rewatch this, and then hopefully when we go over this in the laboratory session, it will start to become clearer to you. But it's a nice technique. It's pretty cool. It allows you to make estimates for what you think might happen. There are literally billions of dollars trading on global insurance markets, so insurance-linked securities based on catastrophe bonds. So basically, insurers will buy catastrophe bonds, and it's all linked into the probability of there being a major event where you might lose your money, but because the insurer takes that money to spend, to basically give to people who have been affected. But in the good times, those people who bought those catastrophe bonds are getting paid money each year for having invested in that product. And the point is that while that's a structured financial product, the math that goes into calculating the risk of that particular cat bond, catastrophe bond, can be thought of in this particular way. Okay, so you can take the relative frequency of different event sizes and make an estimate for what the probability of that is them taking place, and then relate that to whether you think it's a good investment or not, or how much the insurer should pay out, or the parameters involved in the catastrophe bond. Okay, great. So this just gives you a little bit of a graphical example for those probabilities we calculated. So for the hurricane example over here, for each of those hurricanes per year hitting Florida, sadly, or the number of potential days that Mason might have to cancel due to snow or COVID. Okay, so let's move on now. We'll cover this in the lab. It's me just explaining again that in R there are different ways for us to access the Poisson distribution, and actually it's the same as before. You'll notice there's 4 different ways to call it, whether you're interested in the density of events, the cumulative probability, the quantile probability, or the random probability. Okay. Let's move on to the normal distribution. So this is called a variety of different things. So it's called the Gaussian distribution after the German academic Carl Friedrich Gauss. And so he's the person who created the Gaussian distribution. It's also more commonly called the normal distribution, based on the fact that it's normally distributed data and it looks like a bell. So that's why we call it the bell-shaped curve. The distribution is continuous. And what's important is you remember from the descriptive statistics that we did, when you have a normal distribution, then your mean, your median, your mode are all going to be equal to the mean. So mu is going to be symmetrical around the mean value. Okay. The variance is sigma squared, and all of the area under the curve represents 100% of the different outcomes that could occur. You'll remember previously we focused on this, so the green distribution just here is the normal distribution. It looks like the shape of a bell. The red version here is a leptochirtic version of the distribution, so it's highly peaked. And then we have the platychirtic version over here, the blue version. So remember, platy relates, it's very similar to platypus. It means, I think it's flat in Greek. I think that's the semantics of it that I covered previously. So this is just to give you an example of those different distributional shapes. Okay, so green here is the one that is the normal distribution. So the probability of selecting any value is approximately 0 because the data are continuous and there's an infinite number of possibilities. We can also find cumulative probabilities, as we will do within this particular session today. And we can use this for precipitation levels or fertility rates, etc., etc. One thing that we do want to do is to be able to use what is called Z-scores, and this is something which we're going to cover within the lab session. It's going to be in the book. It's important for us to recognize that Z-scores are a good way for us to understand the distribution in a very standardized way, so it's abstracting away from the units that the distribution is measured in, and then we're able to think about the distribution of results in terms of the standard deviation. Okay, so when we think about Z-scores, that's the number of standard deviations around a mean that a data point or a set of data may be, and we can use that to understand things about the world. Okay, so to compare different shaped normal distributions, we can standardize each of them so that the mu is 0 and the sigma is 1 using this equation. So if we've got the population parameters, we don't always have the population parameters, so z is equal to x minus mu, so the mean of the population, over the standard deviation, so sigma. In practice, we don't know these parameters, so we would have to use for a sample the z-score is equal to xi, so an observation minus x bar, which is the mean of the sample divided by the standard deviation. Okay, so this is, hideously scary concept. I've been there, I had to learn this 10 years ago. But I'm going to try my hardest to explain this to you, and if it isn't clear, then you can either rewatch the video, or you can watch the labs, or you can follow some of the other video materials that I provide for you. I've emphasized already that z-scores, z-scores are basically relating values within that distribution of outcomes to the mean. So here in this example here on the x-axis, these are this number of standard deviations. So this is the mean here at 0. And then we have 1 standard deviation above the mean, and there's 34% chance that any value will be between 0 and 1 standard deviation above the mean. Then there's a 13.59% chance that any value will be between 1 standard deviation and 2 standard deviations above the mean. and so on and so forth. And what this means basically is that then we're able to even think about the tails of the distribution. So I could be interested in what the probability of an extreme outcome actually might be. So maybe I'm interested in the probability of a very large insurance claim, and it's occurring very, very in the top tail of the distribution of claims, and this could really sink my business because I'd have to pay out all of the money and would basically go bust. We don't want to be in this situation. So I'm interested in those claims that are so large because the hurricane has been so big that I'm basically more than 3 standard deviations away from the mean, and my company's just not reserved enough capital in order to protect against this sized event. And actually, based on the normal distribution, I'm able to calculate that there's a 0.13% chance that I might go out of business in any year because I've not saved enough capital. Okay, so this is how we kind of use this framework. Wherever the data points are located relative to the mean, we can understand this probabilistically and understand where their distribution may be across those sets of values. Okay, so it's a very nice technique for us to be able to say things about the world statistically, and when we're able to say things about the world statistically, we're able to be systematic about the conclusions that we draw. Okay. So I think the important point is that we can use this as a way for future events to assign probabilities to future events. So, I can say, okay, what's the probability of a value in the future falling into any one part of this distribution, okay? And that's really the strength of this. So let me give you an example. Let's run through something. So we can find a corresponding Z value. So how do we find the probability? The old way is basically to use Z tables. So somewhere I have my book. They are in the back of here that you can go and look at. The Z tables are in the back. Let me think. So the normal distribution Z table is on page 303. You can use this, or you can use a computer to help you calculate it. And I've actually just provided a link down here for a Z-score calculator. And we can just take an example question here and we can run through it, and hopefully this will help to clear up this concept. Okay, so let's assume that we have all of the mileage information for all of the cars produced by a particular manufacturer, and the average miles per gallon for those cars is 25 miles per gallon, so not particularly great. Imagine then that within that distribution there's a standard deviation of 3 miles per gallon. My question is, well, what's the probability if I just buy a car randomly that the car averages under 21 miles per gallon? Okay, so what we want to do is we want to understand all of those values that fall down here in this part of the distribution, given the data that we basically have. Okay, so we have the x value, which is the absolute value, which in this case is 21 miles per gallon. That's the data point that we have. We have the mu, which is the population mean. Well, we know this because we know that the number of miles per gallon that the car's average is 25. And then basically we have the sigma value, which is the population standard deviation. So basically that's 3 miles per gallon, okay? And now we've got all of those data points, we can put it into our Z-score formula that we covered within the previous section. Okay, so Z equals X minus mu divided by the standard deviation sigma. Okay, so we can place those values in. So 21 minus 25 is minus 4. Divided by 3, we get minus 1.33, so that's minus 1.33 standard deviations below the mean. That's basically the location of this x value just here. And then what we're able to do is we're able to find the actual z value for that particular quantity. So let me just find this. Let's see if this opens. So you've got the link for this as well. And what I've done is I've just placed the number of standard deviations, so the z-score, in here, into this box. And what I've done is I've calculated the probability that any value might land down here underneath this value, because that's obviously what we're trying to do in this question. We're trying to find the probability of getting a car that's under that 21 miles per gallon value. And actually the probability for that is 0.09. So basically we've got a 9% chance of any data point landing beneath this value that we calculated here, okay? So we've got a 9% chance that the car that you get averages under 21 miles per gallon. Okay, so there we go. That's an example of how we use the Z-score that we're able to create in order to say something robust about the world. So using the statistical information, we're able to say what the probability is of a particular outcome occurring. So that was kind of pretty quick. We covered that. Let me give you another example here. So we're focusing this time on the standard normal distribution of Z-scores. So here's an example. So using the same mu and sigma values that we had before, what miles per gallon value actually represents the 95% mark? So in other words, at what quantile does 95% of the distribution actually fall under that particular value? So I'm going to go back to that graphic which I showed you previously, which I really liked. So this is the normal bell-shaped curve, the normal distribution here. And remember, we have the probabilities of events occurring within these different parts of the distribution. We've got the number of standard deviations on the x-axis down here. And we're interested in the 95% value mark, so that all of the values beneath that mark represent 95% of the distribution. Okay, so I mean, I've just broadly put this red line where we would expect that to be. So obviously up here we've got 0.13% here, 2.5, and then we would expect this to be approximately 5% up here, which makes 95% below the curve. Okay, so what we want to do is find this value. Okay, so hopefully that's fairly clear to you. We want to find all of the area under the curve just down here. So how do we do that? Well, we know that we want to find we want to find the x value, and we want to find that based on the probability of 95% of the values falling under that point. So the first step, therefore, is for us to actually find the z value. So we need to go into our z tables. So we can either go back to the z table calculated before that I showed you for the website, or we can look in the back of the book. We need to make sure that we're making sure that we get the right z value based on what proportion of the distribution is under that amount, whether it's 95% or whether it's just telling us the proportion that falls under there based to the median. So you need to be aware of that. And then what we're able to do is we're able to basically rearrange the equation. Okay, so up here what we have is our equation that we used previously. So x minus let me go back. So x minus the mean over the standard deviation. So here what we don't have is the x, we have the z-score, we have the mean value, and we have the standard deviation. So what we need to do is we need to rearrange this equation, okay? So basically what we can do is, rather than subtracting and dividing, once we've got the mean, we can instead add the standard deviation times by the z-score, and then that's going to help us basically calculate the x value, so the actual absolute value of the process that we're measuring in the underlying distribution. Okay, so this is 29.935 miles per gallon. That represents the 95% mark at which all of the rest of the distribution falls under it. Okay, so all of that distribution falling under this red line here. So imagine that this is the 29 mile per gallon mark. Okay, so just to close then on that, there's these different ways that we're able to access the normal distribution, as I explained previously. So we'll go over this in the lab. You can access the density, the cumulative, the quantile, or the random probability. And each time, basically, we have a prefix based on the norm function name here. So D for density, or P for cumulative, or Q for quantile, or R for R normal. And therefore, we're able to access these different functions for accessing the actual underlying data. So just be aware of some of the notes that I placed here. So the above are based on standardized z-scores. You can give actual distribution mean and standard deviation as arguments instead, fine. But also you can change the tail of the observation for P or Q norms. So we'll do this in the lab, but you just need to be aware, and I mentioned it previously when I was explaining the question, that you need to be aware of what you're trying to measure. So where in the distribution you are. Are we looking for the 95% of values under that point, or are we looking for the 5% of values over that point? Because you need to specify that in the function in order to get the correct, for example, quantile probability. Okay, so we'll cover this in the lab. Probability mapping. So that was a hard part done. Now I'm just going to close off and basically say that we were covering quite abstract statistical methods previously, and they don't really have any spatial understanding. And the point of this probability mapping is that we're able to then take some of those probability estimates and actually put them in some sort of space in order to understand the spatial variability of probability. So this is something that's quite commonly done across a lot of areas. I'll talk about this in terms of risk of flooding, risk of climate change impacts from sea rise, from stormwater, from storm surges, from hurricanes, or in some of the work that I've done, it's actually the probability of you getting a decent cell phone signal. Okay, so this probability for cell phone signal is going to be dependent on your distance from the cell tower, how many people are in the cell, radius, actually trying to access, maybe you're in a really busy place and everyone's on Instagram trying to connect. So essentially, within that framework, you can start to spatially map where you think people have a probability of getting a certain cell phone signal, and that might be affected by your environment. So if you're in a building, your probability is going to be lower because you've got radio waves have to propagate through building materials. Just the same as if you're further away from the cell tower, then you're going to have propagation difficulties with how the radio waves get to you, and you're able to exchange your data. So this is kind of a very specific example to what I do, but you can use these probability maps to, in reality, understand any natural or physical phenomena depending on what you're actually studying. Okay, so whether that's crime density or flood risk. You can create these isoline maps, which basically help to understand the potential spatial incidence of certain probability values. So I mean here this is actually mapping earthquake risk, so it's basically showing the 2% probability of exceedance in 50 years for peak ground acceleration. So I mean you can see in California along the San Andreas fault, I think, that runs down there on the west coast. I don't specialize in earthquakes. So you can see down there there's a huge risk because we know that they have one of the largest risks from earthquake because they're on the plate fault line. This is a nice way to show this type of probability of risk. And actually I've just kind of described here how we were kind of approaching this before in very abstract terms, looking at these very abstract bell-shaped curves or platykurtic-shaped distributional curves. And the reality is what you kind of want to do is you want to do the statistics bit, which is what I've shown here. And then we want to isolate those areas that meet certain probability thresholds. So for example, perhaps we want to look at areas that are most at risk from drought, or maybe we want to look at those areas that are most at risk from flooding. We can then find parts of the distribution here, identify all of those areas that fall into this part of the distribution and then map them. And then when we actually do that, we can use this to make better decisions. We can use this to invest limited resources. So there's a stimulus bill on the way. I'm sure some of you will be aware of that. In that stimulus bill, there's a whole range of different things that the cash is kind of earmarked for. Some goes straight to states and local governments to do different things. Some are earmarked at the national level, like maybe FEMA, the Federal Emergency Management Agency, will get a bunch of money, and that's for flood protection or something like this. So basically, what FEMA will want to know is where should I invest let's just say, where should I invest $500 million worth of cash that I have from the stimulus into protecting and adapting areas at risk from climate change flooding? And therefore, by doing this, we're able to get a map, and that map will show us the high-risk areas, and then FEMA can work out how it allocates that cash down to projects in those spatial locations. Okay? So this is drawing to a close this part of the course. You've got the assignment to follow this week on probability. And sorry, that's my alarm going for my next meeting. You've got the assignment for probability, and you've got the course materials. The midterm exam will be up next week, so we do not have an assignment next week. You'll be doing the midterm exam, so make sure that you get the pre-tests done, which basically set you up to succeed in the actual exam. And then let me know if you've got any further questions. But I hope, ladies and gentlemen, that you enjoyed the first few lectures of this particular semester for this course, GGS300. I hope that it hasn't been too intimidating for you and too scary. And if you are still struggling with some of the concepts or the assignment homework or working in R, then please reach out to me and I'll try my best to assist you. So anyway, have a very good day, and I will see you all again soon. Thank you.